Welcome again to Math Essential Vector Calculus. Today we are with an introduction to Maxwell equations. In the past videos we have actually studied this, so we just summarize here that Gauss law statement, which is phi E equal Q, means the flux, electric flux, equal to the enclosed charges. And in case of Gauss law for magnetism, we have no magnetic charge, so the flux equal to 0. The third law is Faraday's law of induction, and it mentions that the electromotive force, this one, equal to the rate of change of the magnetic flux with opposing direction. And finally, Ampère-Maxwell law, which maintains that the magnetic field around any closed loop equals to the enclosed current. And we have two types of current. One is conduction current and one is displacement current. And this one we will have the derivative with respect to time, and we multiply here and here by mu because we are using the magnetic flux density, not the magnetic field. So what Maxwell have done is that he brings these four beautiful laws and put together, and we have application of divergence theorem and Stokes theorem such that we can have differential form. So we started with phi E equal Q. We reached this one is basically the Q, this one is simply phi E, and then we applied divergence theorem and we reached that D equal to rho V, and after that we also used phi M equal 0 based on Gauss law of magnetism, and this is basically phi M, and we don't have any enclosed magnetic charges. This is not available in nature. And finally we applied again Gauss theorem and we reached that blah dot B or div B equal to 0. So here we applied the divergence theorem. Here we applied the theorem. Based on this one, electromotive is this part, and this one we used phi M equal to double integral of P and ds. For that we use the derivative inside, and applying Stokes theorem we reach that curl E equal to minus partial B by partial T. And finally for Ampère law, again we used double integral for surface current density to represent I enclosed, and for phi E we applied double integral of D dot N ds, and then we use the derivative again. And finally we have mu outside, so basically we are just substituted with the equivalent, so we got the Maxwell integral form of this Ampère-Maxwell law. And finally we apply the Stokes theorem to reach this relation, which is nabla cross P or curl B equal to mu multiplied by J plus partial D by partial T. So why we use this one, why each of this important? Normally if we want to look to the big picture, we will look to the integral form for global intuition. But if you want to go to the details at some specific local point, we need the differential form. And actually, beyond this one, differential form actually is very important in many things. For first, of course, again, it describes the local field behavior. It leads to what's called EM wave equation, we study in the applied electromagnetic course, which I'll do later. And we have basics for all simulations tools which are available commercially, and even if you want to make your own simulation tool, so you need the differential form. And yeah, it there we can use also the boundary conditions. So this position, Stokes theorem and divergence theorem are essential foundation to reach, because they helped us to reach the differential form. So let's wrap up. Here we have summarized the Maxwell equations. We have explained why differential form is needed. And starting next, I'll move to new playlists, applied electromagnetic and antennas.